we have already discussed in the image. We are first in the first layers, we are extracting the edges, and later a small parts of the face, and finally the facial information can be known such that we can recognize who is there in that photo. Example, take this photo, and we want to extract the vertical edges. This is the vertical edges information, and we want to extract the horizontal edges. This is the horizontal edges information. Now, how we will extract vertical edges and the horizontal edges, that we will discuss now. Let's take example this as an image. Each square box is representing the pixel information. Now we want to detect the vertical edges in this image, which is 6 by 6 pixel. For detecting the vertical edges, I am taking this filter. This is a 3 by 3 filter. We already discussed. Filter can also be called as a kernel or window here. Because I am interested to detect the vertical edges, left column I have kept all ones, and the right column all are minus ones, and middle column zeros. This filter is capable of detecting vertical edges. Let's see now how it will detect the vertical edges. Now we are performing the convolution operation. What is this convolution operation? This convolution operation is nothing but it is simply multiplying this information with this information. So the 3 by 3 filter, when we each element of this 3 by 3 filter is applied to 3 by 3 of this image, then we will get, example, we are multiplying 3 into 1, it is 3. After the multiplication, this is the result. After the multiplication, 3 into 1, 3, plus 1 into 1, and 2 into 1, and 0 into 0, 5 into 0, 7 into 0. So each and every element we are multiplying 3 with 1, and 1 we are multiplying with 1, 2 we are multiplying with this 1, and similarly we are multiplying 0 with this 0. We are multiplying 5 with this 0, 7 with this 0. After the multiplication, we are adding all the multiplied values we are adding. Finally, we are getting the result as minus 5. This minus 5 I have kept here. Now we will shift this filter by 1 pixel, and we will do the same operation again. So when I perform the same operation, when I consider this portion of the image, when I perform the convolution operation with the filter, then the result is minus 4. Similarly, when I take this one, the result is 0. Finally, when we are applying to this portion, the result is 8. Like this, we are also performing in the next row. This what we call as it is moving the filter. Now we have applied with a stride one, just we are moving next row, and then we are applying. Finally, the result is this. So this is indicating that we have taken a 6 by 6 filter, but after applying to a filter which is a 3 by 3 filter, what we are actually doing with the filter, we are multiplying the elements of the filter corresponding elements of a particular portion of the image, and after the multiplication we are adding that, then the result we are taking here. So now this is a 4 by 4 image. You can take, we will generally call it as a feature map. So as of now, you can think this is an image which is reduced to 6 by 6 image is reduced to 4 by 4. Actually, we are taking image is nothing but a group of pixels we have represented here, 36 pixels, each pixel giving the information in the range of 0 to 255 value. Now the features you observe here, only we have 16 features here. So the number of features are reduced. Now consider another image which is having same 6 by 6 size, and we are applying this vertical edge detection to this image. You can observe this portion, the left side portion of the image is having the values 10, 10, 10. The right side portion of the image is having the values 0. So compare it to the left side. Right side we have a little bit dark color because there is we are taking zeros. If we take minus ones, then completely we will represent it using black. So this is a grayscale image. We have represented each pixel value. Now when we are multiplying with the filter, this is the result. When we are multiplying with the first example, this is the first 3 by 3 portion of the image. Then when we are multiplying, the result is 0 because 10 into 1, 10 into 1, 10 into 1, 0 into 0, 0, 0, and then minus 10, minus 10, minus 10. So the result is 0. After the multiplication, or we can after the multiplication of elements in a particular portion, in this particular portion of the image with the filter, then we are getting the result as 0. Now we are shifting, we are taking this portion, and again we are performing the multiplication operation, and then we are adding. We generally call this as a cross correlation. Convolution does not mean the signals and systems convolution we learn. This convolution in the deep learning means we are multiplying the elements, and after the multiplication we are adding. This is similar to the cross correlation we learn in the probability. Okay. Now finally, this is the feature map. 6 by 6 image we have taken, we have applied to a 3 by 3 filter. Finally, we have got this feature map, which is indicating the information in the middle 2 columns. The filter you see here, I have represented with a different color. One I have represented with white color, and 0 little bit shaded gray color, and -1 means it is black color. This is the output we are getting, the 0, because in between 2 columns of zeros we have values 30. This is a white, I have represented with white, and finally this is a shaded color. This is how it is detecting the vertical edges. Now it has detected the vertical edges. We can take another image, second input. In this we are having tens on the right side and zeros on the left side. So when we use the convolution operation with the filter, the resultant we are getting 0 and -30 and 0. Now we are representing this with a black color because this is -30. So this is how, by using a filter, randomly we have taken values 1 for the filter 1, 1, 1 and 0, 0, 0. We are calling this as a vertical edge filter, vertical edge detecting filter. Similarly, we may have horizontal edge detection filter. For the horizontal edge detection, we are taking the filter in this fashion. Ones in the first row, zeros in the second row, and -1s in the third row. If we apply this filter to our input image, then it is capable of giving the horizontal edges. Now you observe, when we applied this filter to the input image, we are getting the horizontal edges information. The first row and final fourth row values are 0, but in between the first row and fourth row, we have the values which is indicating that this is a horizontal edge detector. There is no mandatory that we have to take every time to detect the vertical edges 1, 1, 1 and -1, -1, -1 only. We can take a 1 to 1 or -2, -1, -2, -1 also. This type of filter is called a Sobel filter. This is also capable of detecting the vertical edges in a given image. And we have scare filter 3, 10, 3, -3, -10, -3. Like this also we can take for detecting the vertical edges. So in general, we are taking an image, input image, and we are applying a filter to it in order to get the feature map. What are the values of the filter we have to take? In the Keras, when we are applying a filter, the values, the initial values are given by the Keras only. When we use the Keras Conv2D layer, In this, we have an option called Kernel Initializer. This Kernel Initializer, this gives the chance to us to select the initial values of the weights. But by default, when we do not use this option, by default, the weights are initialized by using Glorot uniform. What is this Glorot uniform method? It is indicating that the initial weights are randomly chosen in between these two values, 6 by n in plus n out minus 6 by n in plus n out. Between these two bounds only, the initial filter values, the initial parameters of the filter can be chosen, and they are chosen randomly. Once they have chosen randomly, every time we are training with the input image, when we are training with the input image, every time with respect to the error, by using the back propagation method, these parameters of the filter are updated. Only at the initial stages only, by using this Glorot uniform method, the filter parameters are initialized in between two limits, and later, because of the training process, based on the error we are getting, depending upon the error, by using the back propagation method, these filter parameters are updated accordingly, such that in future, when the model is ready, when the model is trained, it is the filter parameters which are capable of extracting the information features from the input image can predict in the final layers after the fully connected dense layers. That can be, this CNN is used to predict a particular cat in that image or particular object in that image, or even we use for the neural style transfer. That is how we initialize the filter parameters by using the Glorot uniform in normal. There is no need to mention this. If we are not mentioning this, by default, these parameters are chosen by using Glorot uniform. If you want to give the filter parameters manually, then at that time you should not use this Glorot uniform. You can input the filter parameters. And here the filters is indicating that number of filters you are interested to take, whether we are taking 2 filters, 4 filters, or 8, 16. In generally, we start from the 16, 32. The filters we usually take in the 2 to the power some n format, either 16 or 32 or 64, 128 filters. This is the kernel size, which is indicating what is the size of that filter. Generally, we take 1 by 1 or 3 by 3 or 5 by 5 or 7 by 7, like that. In generally, when we are taking the input image that is less than 128 by 128, then 3 by 3 kernel is sufficient. So we have to give here in the kernel size 3 comma 3. It is a tuple data type. So these two values, 3 and 3, are indicating that we are interested to take a kernel or filter of size 3 by 3. This is the input image, and we are taking the small portion of the input image. This is our filter. We are also calling as a feature detector. We are multiplying the elements of this filter with a portion of the image, and finally we are getting the feature map values. This is how we apply this filter to the entire image. Now you can observe the same thing in the three-dimensional way in order to understand properly. We are multiplying 9 with 0 and 1 with 4 and 1 with 1, and similarly 4 with 2. Similarly, the corresponding elements of the image with the corresponding elements of the filter, and finally we are adding all those multiplied values. Finally, we are getting the result 16. This output array is called as feature map. This is filter. The values of filter are initialized by using the Glorot uniform. Later, these values of the filter are updated depending upon the training we are giving. We should always take filter size in odd only, like 1 by 1, 3 by 3, 5 by 5 or 7 by 7. We mentioned already, when the input image is less than 128 by 128 size, then 3 by 3 filter is sufficient to extract the features. If it is having more than 128 by 128 size, then we can choose up to 7 by 7 filter, which is capable of handling, which is capable of extracting the features from the input image. Now you can observe here, we have taken a vertical edge detection filter, and we have multiplied the elements of this portion of image by using our filter. Finally, we are getting the value 6. Similarly, when we apply to the next portion of the image, we are getting -9, -8, -3, -2, -3, -3, 0, and -2. This is how we are. This is how our filter is shifting. You can observe the transition of the filter. This is what we are calling as, it is striding by 1 pixel. You can observe each and every time it is striding, corresponding value of the feature map we are getting. This is a 5 by 5. This is a 5 by 5 input image. When we convolved with 3 by 3, when we applied the filter, 3 by 3 filter, then finally we are getting a 3 by 3 feature map. Here you can observe we have taken another 5 by 5 input image. The filter this time, in order to make it convenient, you can observe the filter, how the transition of the filter is taking place. And similarly, we have taken another. Here the filter we have considered is 0, 1, 2, and 2, 2, 0, and 0, 1, 2. We are multiplying the values of the filter. And finally, we have got the feature map. Now, this is another example where we have considered 5 by 5 image. When we applied the 3 by 3 filter, we are getting a feature map, 3 by 3 feature map. Here we have considered a 2 by 2 filter, and the input image is 5 by 5. And finally, we are getting a 4 by 4 feature map. The filter we have considered is 0, 1, and 1, 2. We are multiplying the 0, 1, and 1, 2 with each 2 by 2 size of the matrix in order to get the feature map. This is what actually we are doing. We are taking a 3 by 3 filter, and we are multiplying the corresponding elements, and after that we are adding, then finally we are getting the feature map. Assume I have considered the filter this time is a eye filter, which detects only eye. You can observe where the human being eye is there in that image, there we are getting 100, and in all other portions we are getting 0. This is an indication that the filter we have considered is capable of extracting the information of eyes. This is how we take the filter. Now we want to know the size of the feature map. Now we want to know what is the size of this feature map. We know the input image size is 6 by 6 and the filter size is 3 by 3. How to get the feature map size by using these two? We can get, if we take this as n by n, input image size is n by n, and the filter is f by f, then the size of the feature map is given by n minus f plus 1 by n minus f plus 1. That means we are simply subtracting 3. We are simply subtracting 3 from 6, and then we are adding 6 minus 3 plus 1. This is nothing but 4 by 4 is the feature map matrix size. That means if we would have considered 1 by 1 filter, then the feature map matrix size is 6 minus 1 plus 1, means same 6 by 6 matrix we will get. And if we consider a 5 by 5 filter, then the feature map matrix size is 6 minus 5 plus 1, which is indicating that 2. Then the feature map matrix size is 2 by 2. This time the input image size is 7 by 7, and the filter or kernel size is 3 by 3. And the feature map matrix size is 7 minus 3 plus 1. So this is 5 by 5. Now we have considered an input image 5 by 5. Filter we are taking 3 by 3. The feature map matrix size is 5 minus 3 plus 1. So it is 3 by 3 matrix. Now the input image size is 5 by 5 and the filter size is 2 by 2. So 5 minus 2 plus 1. So output feature map size is 4 by 4. Now we are observing the practical implementation of the filter in the Conv2D layer. Here we have filters equal to 64 and a kernel size equal to 3 by 3. The input image we are giving 28 by 28 input image. So 28 by 28 input image. So input image is 28 by 28 and the filter we are considering is 3 by 3 filter. We are considering 64 filters. So we will get the 64 feature maps. Each feature map size is 28 minus 3 plus 1. So it is 26 by 26. 26 by 26 feature map we will get, and the number of feature maps are 64. Now you observe here the output shape 26 by 26 feature maps. Size of the feature map is 26 by 26, and how many feature maps we are getting? 64 feature maps, because we have applied 64 filters. Now we will change the kernel size to example 5 by 5. When the input image size is less than 128, we never suggest to take the kernel size 5 by 5. But in order to explain the different ways how we can give the kernel size, now I have considered 5 by 5. Okay, the input image size is 28 by 28. And this time we have taken the kernel 5 by 5. How many kernels we have considered? 64 kernels. And finally, the feature map size is 28 minus 5, 23. So we will get 24 by 24 if we execute this one. 24 by 24, 64 feature maps we are getting. Okay, we will execute this one. So shift plus enter and shift plus enter. You observe here 24, the feature map size 24 by 24. And how many feature maps we are getting? 64 feature maps we are getting. And we will change one more time. This time we will take the kernel 7 by 7. So I am considering a 7 by 7 kernel. So 28 minus 7, 21 plus 1, 22. Now if I execute this one, I am getting my feature map size is 22 by 22. How many feature maps I am getting? What is the number of filters I am giving? That many feature maps I am getting. Now what is this number 3200 parameters is indicating? This time I have taken 7 by 7 filter. So 7 by 7 filter means 49 parameters, filter parameters. And how many such filters I have considered? 64 filters. So 64 into 49, it is 3136 parameters. Plus I am taking for each filter one bias parameter. So 3136 plus 64, which is nothing but 3200. And we have already discussed how we initialize the values of this filter by using the Glorate uniform. So that's why kernel initializer I have not mentioned here. I have left the choice to the Keras. Every time these parameters will be updated based on the error we are getting, based on the training we are giving. This 3 by 3 size we are giving in the tuple. This is what this, when we define a data type in Python by using these open braces, we are calling that as a tuple data type. Because the two height and width of the filter is same, we can even, instead of 3 by 3, we can even mention simply 3, which means that it is a 3 by 3 filter. But it is a standard procedure to mention 3, 3, such that we can understand this is a 3 by 3 filter. This is how we implement the number of filters and the kernel size in the Conv2D layer.